Hi there, this is the second lesson in the momentum series. So this is momentum concepts, impulse and force time graphs. It's not a very long video, it's quite a simple topic, but it's obviously very important that we know this. So impulse, or the change in momentum. So impulse is equal to the change in momentum produced by a force over a period of time. A little bit strange, but much easier as the equation. So we have the equation force is change in momentum divided by change in time. If you rearrange that to get change in momentum is force times time, that is the impulse. So impulse is also equal to the change in momentum. It's measured in Newton seconds, but because it is the change in momentum, it's also measured in kilogram meters per second. Okay? Kilogram meters per second and Newton seconds are the same thing, same unit. So force time graph. If you have a force time graph, so I'll just draw a random one. So force in newtons against time in seconds. So it could be anything, maybe something like this. The area under the graph is equal to the impulse. Because if you look at the area under the graph is force times time. And we just established that force times time is the impulse, which is also equal to the change in momentum. And remember, impulse is measured in Newton seconds, or the equivalent is kilogram meters per second. So let's move on. What you can find when you get these questions typically is you can get like solid shapes. So it might be a rectangle or a square, or you might get something like this. And then you have to have a compound shape. You have to calculate two areas separately, this first area and the second one. But more often than not, you will get something like this graph on the left. And what you have to do is count the squares. And normally in your exam, so in this example, it says that the area under the curve, there's 9 total blocks. In your exam, it might say, anything between 7.5 and 10.5 blocks, or it might say between 8 blocks and 10 blocks. Depends how easy it is. So let's have a look at this example. So that's 1 block, 2 blocks, 3, 4, definitely 5. This one and this one probably equals 6, 7. This one's nearly 8, 8.5. So I would go with around 8.5 blocks. Or you might come to the understanding that this one might equal 9 blocks. You will get a range. So let's go with the 9 blocks. So the force times time for 1 block, so as you can see, would be, let's get rid of this, make some room. So 50 newtons, so 50 newtons up and 1 millisecond across. So each block would be 50 times the 1 millisecond. So that'd be 5 times 10 to the minus 2 newton seconds, or kilogram meters per second. And then we just multiply by the number of blocks. So the total change of momentum, or impulse, for this graph in particular, is 0.45 newton seconds, or 0.45 kilogram meters per second. Remember, the impulse is equal to the change in momentum. So let's have a look at some examples. So quick graph question. So calculate the impulse and the change in velocity caused to a mass of 5 kilograms from the graph opposite. So if you want to pause the video, have a go. So remember, the area under a force time graph is the impulse, or the change in momentum. So this is simply 3 high and 3 across. So the area gives us the impulse of 9 newton seconds, or 9 kilogram meters per second. And remember that the impulse is equal to the change in momentum. So force times change in time is equal to the change in momentum, which in this case is just mv. because we're looking at the change in velocity. So force times change in time is 9 equals a mass of 5 times v. So v would simply be 9 divided by 5, which is 1.8 meters per second. Let's look at the next one. Next one's a compound shape, still very simple. So this one says, a body initially at rest of mass 8 kilograms undertakes motion according to the graph below. Calculate the final velocity of the body. So if you want to pause and have a go. So essentially what we need to do is to calculate the impulse from the graph. We've got a force against time graph. And we've got a compound shape. So we've got a triangle and a rectangle. So 2 areas. So the first area is 8 times 3 and then half it. So 24 divided by 2, 12 Newton seconds. And then the next bit is 3 again, 3 times 8, which is 24 Newton seconds. And then just simply add them together. So the total impulse or change in momentum is 36 Newton seconds. So we've got the force times time equals the change in momentum. So force times time is 36 equals the momentum's mv. And we've got 8 times v. So the final velocity will be 36 divided by 8. So that gives us a velocity of 4.5 meters per second. Pretty straightforward, should be okay. Let's just do one more example. Let's get rid of this and move on. So this time, same questions, basically different numbers, but this time we've got an initial velocity. So if you want to pause and have a go, and then I'll take you through the answer. So on this one, a body initially moving at a velocity of 20 meters per second of mass 6 kilograms undertakes motion according to the graph below. Calculate the final velocity of the body. So same as last time, we've got compound shape, so 2 shapes. So the first one is a triangle, so 8 times 4 divided by 2. So that's 16 Newton seconds. And then we've got the rectangle, which is just 4 by 8. Which is 32 Newton seconds, which gives a total of... So we've got 48 Newton seconds in total. So force times time is the impulse, which is equal to the change in momentum. So the force times time is the 48 equals, this time we've got an initial velocity and we want the final velocity. So we have to do mv minus mu. So I'm going to do I'm going to factorize v minus u. So 48 equals, we need 6, the mass is 6. So on the left hand side we end up with 48 divided by 6 equals final velocity v minus the initial of 20. So if you do 48 divided by 6 in your calculator, we get 8 equals v minus 20. So we need to move the 20 over, so it becomes plus 20. So v is 28 meters per second. Pretty straightforward topic area to do with momentum. Hopefully that went okay. Hope you liked the video, and I'll speak to you soon. Thank you.